Hi, my name is Pouya, and today I want to talk about our paper that appeared in CP2023. It's called SAT-based learning of compact binary decision diagrams for classification. First, just to talk about the motivation behind the paper, we know that decision trees as interpretable classifiers, they have good accuracy and they are compact and easy to understand. However, there's one shortcoming. Their number of splits grows exponentially in the depth of the tree. In order to address that, which causes a lot of issues, for example, data fragmentation or overfitting or size for applications that are very sensitive to size, or cause issues for interpretability as well. In order to address that, we use BDDs as more compact alternatives to decision trees. And they are more compact because they employ the same split across each level, leading to a linear number of splits in the depth of the diagram. Our contributions are as follows. We propose a SAT-based encoding for learning max accuracy BDDs. We model the size of the BDD as a secondary objective, which we can optimize in addition to accuracy. Next, we introduce and model a new family of BDDs called multidimensional BDDs, which are more expressive alternatives. And lastly, through our experiments, we show improved compactness while maintaining accuracy for BDD classifiers. In terms of the background information, there are two things that we need to go over. The first are BDDs themselves. What are they? They are rooted directed cyclic graphs, and they are mostly used as representations of Boolean functions. Historically, they come from the hardware synthesis literature. There are a lot of work in that area, but recently there has been a focus on using BDDs for classifiers, or more specifically interpretable classifiers as well. In terms of the components, the nodes are divided into two groups. We have terminal nodes, which are the leaves, and the rest are called decision nodes. Each decision node is labeled with a feature and has two outgoing edges, one corresponding to the value of 1 for that feature and the other one corresponding to the value of 0. If we want to classify a point, we enter the point from the top. Based on the feature and the value, it goes to left and right and continues to do so until it reaches a leaf. And the label that we give to the point is the label of the leaf that it ends up in. And we can have more than two leaves as well. In that case, it's called the multi-terminal variation of the BDD, and this is the variation that we focus on in this paper. There are two important properties that BDDs can have, being ordered and being reduced. Ordered means that if we go from the top to any of the leaves at the bottom, regardless of the path we take, there's a total ordering of features that is respected. So for example, on the left, we see a BDD that is not ordered because for some of the paths, we see x1, x2, x3, but for others, we see x1, x3, x2. But the one on the right is ordered. In addition to being ordered, a BDD can be reduced, which means that we have eliminated all of the redundant decision nodes, and we have merged all of the equivalent decision nodes. And this is always unique. So if you have a BDD that is ordered and reduced, independent of how you did the reduction, you'll always get one thing. So for this particular example, we see the one is the unique form of the reduced BDD that we are discussing. The other part of background information that I wanted to discuss was the max SAT paradigm. We know SAT. In SAT, we have a set of binary variables, and we have a set of clauses that are subset of literals, meaning either those binary variables or their negation. We are trying to find an assignment for those binary variables that satisfies all of the hard clauses. But in MaxSat, in addition to those hard clauses, we have the soft clauses that are not guaranteed to be satisfied when we find a solution, but we want to satisfy as many of them as possible. And that's the optimization aspect of MaxSat, and that's why it's an optimization paradigm that we can use in our setting to learn BDDs. Now, on to the encodings themselves. We have multiple encodings in our paper. For each one, I first discuss some of the few highlights, and then we go into the details of what the encoding is and how it works. So for the first one, we're just trying to learn a BDD that is maximum accuracy. So we postpone any size consideration that we can have for further encodings. Two aspects that I wanted to highlight. The first one is that we use a direct encoding of numerical features, the ones that we introduced in our previous work. This means that in each split of our BDD, the feature and the threshold is being learned. The alternative to this is that we can binarize all of the features in advance, but the downside to that is that there will be an excessive number of features which we have shown in our previous work that can cause issues for performance. The second aspect that I wanted to highlight is that our encoding learns BDDs that are ordered, but not necessarily reduced. So on the right, you see something that we can learn from our algorithm. And what can happen is that for some of the leaves, in this example, this one here, highlighted by question mark, they might not contain any of the points in our training data set. And because of that, it doesn't matter whether their label is 0 or 1 or any other thing. It doesn't affect the training accuracy. So when we have learned this and we're trying to reduce it into the reduced form, we have to make a decision on the labels that we are trying to assign to these empty leaves. And based on that decision, it might affect the size of the reduced BDD that we get in the end. So we do reduction in the second stage, but you have to make these decisions with regard to the empty labels. And this is something that we can come back to when we discuss size optimization. Now, on to the details of the encoding. I won't cover everything in detail, but I just wanted to give you a high level of how it works. We have a set of variables. The first ones model what feature is selected at each step, at each split rather. The second one tells us what happens to each point at each split, whether it goes to left or right. The third set decides how labels are assigned to leaves. And the last one and the last set of variables represent whether points are being correctly classified or not. And for hard clauses that we have in our encoding, I've divided them into groups. The first group guarantees that exactly one feature is selected at each split. The second group guarantees that once that feature is selected, the way we divide the points into going to the left and going to the right respects that feature. So it can actually be a threshold and a feature that is dividing the points. The third family makes sure that exactly one label is selected at each leaf. And lastly, the fourth family tells us if we are claiming a point to be correctly classified, the label that the point has needs to be the same as the label of the leaf that the point ends up in. And lastly, for our soft clauses, we're basically just trying to maximize the number of points that are being correctly classified. Now, on to the second encoding. In this encoding, we want to add size consideration and the optimization of size as well. How can we do that? In our previous encoding, we saw that we learned unreduced BDDs, but then reduce them to get the unique compact form. But if we want to optimize the size as well, we need to somehow encode what happens in that reduction. So we need to model what we are modeling in our objective is the size of the BDD after it's reduced. But how can we do that? What it comes down to is basically asking two questions for each of the decision nodes. The first one is, can it be replaced by one of its children? Because if it can be replaced by one of its children, it means that it's redundant to have that both. We can just eliminate it. So on the example on the right, we see that the node at the top can be replaced by one of its children because the two children that it has are identical. They use the same feature and they have the same labels at the bottom. So we can just simply, that decision that is happening at the top node is redundant and we can eliminate it. The second question that we can ask is that, can it be merged with one of the previous decision nodes in the same level? So this is basically the question of equivalency. If it can be merged and if it's doing the same thing, then we don't need it. We just need to have one point to be the representative of all the sets that are equivalent to each other. And in our example, we see that for the top one, it cannot be merged because it has no previous nodes. The same thing happens with the left node, but with the right node, it can be merged with the left node because they're doing the same thing. They have the exact same set of labels at the bottom. So the question for that particular node is yes. And if we do this, if for the decision nodes that one of these questions has the answer yes, we can basically say that these do not belong in the reduced form and they are being eliminated as part of being equivalent to something else or being redundant. So the size of the reduced version that we get in the end is the number of decision nodes that have the answer no to both of these questions. And that's how we encode the size optimization objective. And we can, once we encode it, we can use it in two ways. It can be either one stage, which means combining it with the accuracy objective and optimizing them at the same time, or it can be two-stage, which means that we learn the accuracy objective first, and then as part of the reduction post-processing step that we discussed, we use the size optimization as a post-processing step to decide the labels of the empty nodes that, as we discussed, can affect how compact our BDDs can be. And this is the encoding. Again, I'll give you a high-level explanation of what the variables and the clauses are. The first set of variables are the alpha variables, and they're basically modeling the difference in labels. And this is needed because we want to detect redundancy and equivalency. The second set basically tells us if a decision node can be replaced by one of its children. So if the two children are exactly the same, this decision is not important, is redundant, so it can be replaced by one of its children. And the third set of variables model whether two decision nodes at the same level are equivalent. So it looks at the sequence of labels at the bottom of each of these decision nodes, and if they are the same, it tells us that they are the equivalent ones. And for our hard clauses, we first need to guarantee that the alpha variables are being correctly modeled. Secondly, we need to say that if the B variables is indicating that the decision node is redundant, then the two children need to have the same set of subsequent labels at the bottom. And the third set of hard clauses does the same for our third set of variables. It tells if the two decision nodes are being claimed to be equivalent, the set of labels at the bottom need to match. And for our soft clauses, we're simply maximizing the number of decision nodes that have an answer of yes to either of the two questions that we discussed. So it's either being replaced by one of its children or being merged with one of its previous nodes at the same level. For a third encoding, we come from a different perspective of trying to optimize the size. Here we are introducing a new family of BDDs, and it can help with the size because they are more expressive within the same depth. So we don't have to increase the depth and then optimize the size. Within the same depth, we are introducing something that's just more expressive, and that helps us with size optimization and accuracy. Our suggestion is that instead of using ordinary splits, which are just thresholds and features, we let the splits be dictated by directional inner BDDs. So we have an BDD inside our BDD that tells us whether our points are being directed to the left or to the right. And the split that this kind of mechanism is behind it is called the multidimensional split. And the BDD that uses multidimensional splits is called the multidimensional BDD. So just to give you an example, first of all, a directional inner BDD has a dimension, which is basically its depth, and has terminals representing left and right by values 1 and 0. So if a point is entered into this inner BDD and gets a value of 1, is being directed to the left, and for 0, vice versa. Just to give you an example, this is an example of an empty BDD. It looks like an ordinary BDD, but instead of having a feature label for each of its decision nodes, in each decision node, there's another BDD that it can operate on. So for example, we see that T0 is itself a BDD that uses 2 features. And T1, again, is itself a BDD that uses another 2 features. And you can observe here that even though seems like a complicated structure, it can all be translated to an ordinary BDD if we just use all of the features that are being used in the inner BDDs. So in this example, we can just have x1, x2, x3, x4, and make an ordinary BDD. But we argue that using these multidimensional BDDs are still of benefit, because when we use this, we can have the expressiveness in a compact size, rather than, let's say on the right, we have a depth of 4, and when we learn a BDD for a depth of 4, we have to deal with the exponentiation to the power of 4. But if you're learning the one on the left, that becomes unnecessary. And this is where the power of empty BDDs come from. Now on to the encodings of these new family of BDDs. It looks very complicated, but it's very simple. So we just basically have to have all of the components that we had for encoding a BDD. We push it into a box, And we use it for each split in our MD-BDD because each split is another BDD. And after we do that, we need to have a layer on top that basically takes care of the classification techniques. It makes sure what happens to each point at each step and whether the points are being correctly classified and so on. So again, here it looks a bit more complicated, but it's all the stuff that we already had before. The hat versions of the variables are basically the same variables, but right now they're being used for inner BDDs. So we have variables for feature selection, for what happens to each point, whether it's being directed to left or right, and for choosing labels at the leaves. And the same goes with hard clauses. One feature is selected. The selected feature enforces the order of values, and the value of a multidimensional split matches the label of the containing leaf in the BDD. This is basically the inner classification that is happening. And at the end, we also have a symmetry breaking clause, because it doesn't matter if we divide the 2 points into 2 subsets. It doesn't matter which subset we are directing to the left and which we are directing to the right. So adding these simple clauses just makes sure that we're breaking the symmetry and hopefully improving the performance. And in addition to all of these things that we are keeping hard clauses and soft clauses from before. And those are the parts that dictate the overall classification that happens. So again, what happens to each point and each multidimensional split? And once it reaches a leaf, if we are claiming that point to be correctly classified, it needs to have the same label as the leaf. And that's basically the encoding for MD-BDDs. Now, one interesting theoretical result that I wanted to share was that we already saw that multidimensional BDDs on S splits, if the sum of the dimensions are D total, they can be transformed into an ordinary BDD on D total ordinary splits. And that tells us that the second family that I just described is more expressive than the first. This is the relation that you see on the screen. But we have the other part of the relation as well, and that is trivial as well, because multidimensional splits are inherently more complicated, more expressive. That tells us that an MD-BDD on S splits is more expressive than an ordinary BDD on S splits. So this is kind of a nice sandwich of MD-BDD's expressiveness between the expressiveness of 2 ordinary BDDs. And it would be interesting in the experiments to see if this happens in practice as well, or is it just purely theoretical? Now, on to the experiments. The first thing that I wanted to talk about is what are we looking for in our experiments? What are the questions that we are trying to answer? The first one is, well, is our approach improving the state of the art in terms of performance, meaning runtime and training accuracy? The second thing that we want to see is that do 1-stage and 2-stage approaches improve compactness, first of all? And if they do, how do they affect testing accuracy? Does improving compactness come at a great cost to testing accuracy or not? And lastly, for our MD-BDDs, we want to see if their unique structure is enabling us to employ a higher number of features in our solutions within the same compact size. The setup is that we are using the baseline. That is a very recent baseline, and it learns max accuracy BDDs. It's different from our work in two ways. First of all, it does binary classification, not multi-terminal, and it does prior binarization of features rather than a direct encoding of numerical features. For our data sets, we chose 11 data sets from UCI, and we tried the data sets to be diverse in terms of size and application. And for solver, we chose the Loandra solver with a 15 minutes time limit. The first set of results is focused on performance. We see that we are able to get higher training accuracies and shorter run times compared to the state of the art. And the surprising part is that the improvements does not only happen for highly numerical data sets. So for example, in this table, you see that for the Monk2 data set, which is a mostly binary data set, there are a small number of potential values for each feature. You're still getting a very significant boost in terms of runtime. And that was surprising to us because we mostly expect the improvement to happen because of the direct numerical encoding and for highly numerical data sets. For the second set of experiments, we focus on size optimization. First of all, in contrast to what we did for the performance results, we use five-fold cross-validation because we want to study testing accuracy as well, and we want to study how compactness affects generalization. We have a parameter, beta, that controls how we balance the objectives of size and accuracy against each other. If it's a real value, it is basically the weight of the accuracy objective. If it's infinity one, it's the same exact one-stage approach. They're being optimized simultaneously, but accuracy is completely prioritized over size. If it's infinity two, it's the two-stage approach, meaning that we learn max accuracy BDDs first, then we try to optimize the size by deciding the labels of the empty leaves. And if it's the default approach, there are no size optimization at all. So here we see the size of our solutions that we were able to produce. And we see that one-stage and two-stage approaches significantly improve compactness compared to the default approach. And we see that the biggest jump happens from default to the two-stage approach. If we include size in the first stage as well, sizes go down incrementally as well. But the biggest jump is from default and the two-stage approach. And the second stage that we do for size optimization doesn't take a lot of time, and it doesn't hurt even the training accuracy. So this is basically to no cost at all. We're just achieving significantly compact solutions. And we see that even though we are achieving significant compactness compared to the default approach, the testing accuracy is not being damaged. So we see almost little to no damage until maybe the value of 3 and 1 for beta value. But for all of the first 4 or the 4 to the right, we see that compactness comes, but it doesn't hurt the accuracy. We are maintaining accuracy while getting smaller solutions. Now, on to the third set of experiments that I wanted to discuss, and these ones are focused on MDBDDs. We are again doing five-fold cross-validation because we want to study testing accuracy, and we have a parameter which is the sequence of dimensions, because the framework of MDBDDs is flexible, and you can have for the first level multi-dimensional splits of dimension 2. For the second level can be 3, and for the third level can be 1. It can be completely variable. And here we consider 2, and this is why it's a parameter, because there's no best way of doing it. It might be different for different solutions. Here we consider 2 sequence of dimensions, one that is completely balanced and another one that is completely imbalanced. And one other thing that I wanted to highlight with regard to these results is that we utilize two-stage size optimization for MDBDDs as well. Because two-stage size optimization happens as a post-processing step, it doesn't interfere with the unique structure of MDBDDs, and it basically comes with no cost. So we thought we should use this for MDBDDs too. In the results for MDBDDs, in the results for testing accuracy, we see that our 2 sequence of dimensions that we have, which is 2, 2, 2, and 3, 1, 1, 1, they are both, in terms of testing accuracy, very close to the upper bound of expressiveness that they have. So the upper bounds for these 2 are the sum of their dimensions, right? So for both of them, the upper bound is 6. And the lower bound for this one is 3, and for this one is 4. But we see that for testing accuracy, the accuracies that they get is very close to upper bound. But what happens with size? We see that even though in terms of accuracy, they're really close to the upper bound, they are significantly more compact than the upper bound in terms of size. In fact, they're really close to 5 rather than 6, with 6 being their upper bound. We also studied what happens in the encoding as well. We know that the number of clauses and the length of the clauses are important measurements that we have for deciding how difficult the encoding is and how much it scales when we improve the size, when we increase the size. And we see that, again, for the MDBDD case, the number of clauses is comparable to their upper bound and maybe 5. But the clause length, which is very important for performance based on how SAT solvers work, are significantly shorter compared to 5 and 6 for both of the sequences that we have. And lastly, for MDBDDs, we ran another experiment that was focused on a single data set, which was the adult data set. And this is relatively bigger than all the other data sets that we tried. It has 32K points or 100 features, and we increased the timeout to 60 minutes as well. And again, here we see the measurements of number of clauses and the length of the clauses. We see that for the ordinary BDD case, which is the one-dimensional one, the black line, these two measurements seem to grow exponentially, while for all the other dimensionalities, it's much more manageable across the sum of dimensions as we increase the sum of dimensions. And this is reflected in the solutions that we are able to produce and their accuracy as well. Again, this is just the training accuracy because here we're focused on performance. And we see that for the ordinary one-dimensional case, the highest number of total features that we can employ is 12. But the multi-dimensional features, multi-dimensional MDBDDs, whether it's 2D, 3D, or 4D, allow us to produce solutions that can employ up to 15 or 16 number of features. And this shows that their expressiveness within their compact form is allowing us to look at more features in the data set and have better classifiers. And that was all the experiments that I wanted to discuss. Just to give you a summary of what we talked about today, we proposed a SAT-based encoding for learning BDD classifiers. It employs numerical feature encoding and supports multi-label classification. As a secondary objective, we introduced size optimization that can be used in a one stage, which means combining the two objectives, or two-stage approaches, which means learning for accuracy and then a post-processing step for size. We also introduced a new family of BDDs called multi-dimensional BDDs that work with directional inner BDDs and multi-dimensional splits. And we showed that this is an alternative to BDDs that is more expressive within the same size. And we provided theoretical results on how their expressiveness compares against BDDs. And lastly, through our experiments, we showed better performance than state-of-the-art. We showed that we are able to achieve significant compactness with almost no cost to accuracy. We also showed that the compactness that we get helps with better generalization and testing accuracy for our data sets. And lastly, we showed that our MDBDDs, through their unique structure, are enabling us to employ higher number of total splits compared to ordinary BDDs. And that would be all of the things that we discussed today. For future work, there are a few directions that we consider to be interesting. The first one is just allow more control to the two-stage size optimization. Here we just allow it to decide the labels of the empty leaves, but we can also allow it to decide the order of the features, which, coming from the BDD literature, we know it's very important, and it affects the size of the BDD significantly. The second potential interesting idea is to encode nested directional BDDs. So here we just have one level. We have BDDs that operate on BDDs. But let's say the inner BDDs themselves operate on the second level inner BDDs and can increase these to multiple levels. It's not trivial whether that can further help or not, or it might be too much overhead in terms of performance, but it would be interesting to investigate that. We also want to look at more strategies to balance the two objectives against each other. One potential candidate would be to generate the Pareto optimal front of these two, with regard to these two objectives, so that we can look at all of the solutions that look good rather than picking one of them by somehow balancing these two. And lastly, we also feel the need to analyze the effects of dimension sequence parameter more. In this paper, we used two heuristics, namely balanced and unbalanced distribution of dimensions, but more heuristics and more ways of looking at it, maybe a random distribution of dimensions can be used. And it would be very interesting to analyze how different heuristics work and how they compare, and for what data sets should we go for certain heuristics. So analyzing the effect of that parameter is, we believe, another interesting direction to look at. And that is all. Thank you so much for your time. And I can answer your questions by email, since this is not an in-person presentation. Thank you so much.